All right, so in this video, I want to look at another super duper important property of inverse functions. This one is going to pertain to what the graph of them, what the graph looks like. So last time we said that when you compose a function and its inverse, that they cancel each other out and that you're just left with x, all right? That's how you prove that two functions are inverses of each other. You compose them and you get x back as an answer. Graphically, when you look at two functions that are inverses of each other, there's going to be a reflection across the line y equals x. All right, you're going to see a nice reflection that happens. All right, so we looked at last time the 1/2 x plus 6 and the 2x minus 12, and we said, yeah, those are inverses of each other. All right, so you see the graphs of them here. If I go ahead and graph y equals x on the same plane, hopefully you see this nice little mirror image that's going on. All right, they're a reflection of each other across the line y equals x. Okay, and so what that's going to mean as far as the ordered pairs, let me find a good one here. How about this one right here? What is this? 28, 20. Let me plot that. 28, 20. So if 28, 20 is on the red one, that means that 20, 28 will be on the blue one. There it is. All right, point by point, they are just a reflection of each other across this green line. The x and y values are just swapping with each other. All right, that's the idea. And that makes sense that that should happen because that's kind of what we did. We swapped the x's and y's to find the inverse originally. Let me go ahead and look at that as well with our square root function that we had, okay? All right, this was our original red square root one. And if you remember, quadratic one. And then on the inverse of it, which was the square root, remember we had a plus and minus that was going on? There was this square root of x minus 5, and there was also the negative version of it, negative square root x minus 5. All right, so you got the reflection. Hopefully you can see that. And again, point by point, they are being reflected along this green line here. So here we've got 2, 9. So that means on the inverse, you're going to see 9, 2 somewhere. All right, yeah, right there, 9, 2. All right. Now, while I'm here and I've got these pulled up, I want to go ahead and mention something back from Algebra 1, okay? If you look at these two functions, okay, the linear functions, I want to point out the fact that they are functions. I know that seems profound, but a function, according to algebra, was something where when it was something that passes the vertical line test. That was how we kind of summarized it. Everywhere you draw a vertical line on this thing, it only crosses once, right? And if you look at the red one and the blue one, each of them pass the vertical line test. So that means its inverse is a function. What it means to be a function is that every x value corresponded to only one y value. Let's say right here, at 19, you get 15.5. You never ever get confused at 19. Like, you always get 15.5. You don't accidentally get another number sometimes. But if you look at the quadratic one and its inverse, that's not going to be the case. Of course, the quadratic, the original, it is a function. It passes the vertical line test. Everywhere you draw a vertical line, it just crosses at one time. But its inverse is not a function, okay? If you draw a vertical line right here, you see that it's going to intersect twice, all right? And that's because this function, or this relation, I should say, gets confused. If you plug in 30 for x, it looks like you get 5 back. But then down here, when you plug in 30 for x, you get negative 5 back. And that is the single thing that breaks the rule for it being a function. All right. We'll talk more about, we'll give some definitions and summarize that whole talk right there. But that's one of the other properties that's going to be important about inverse functions.